Today's topic is temperature entropy diagram. TS diagram. T is the temperature, S is the entropy. So temperature entropy diagram or TS diagram. For some reversible process, if dq is change in heat at temperature T, the change in entropy ds is defined as ds equal to dq upon T. This is the definition of entropy. Change in entropy is given as ds equal to dq upon T. S is the entropy and ts is change in entropy. dq is change in heat at temperature T, and this definition for change in entropy is for reversible process. From this definition of entropy, we have dq equal to Tds. In this relation, if heat is absorbed by the system, then dq is positive, then ds will also be positive. So if heat is absorbed by the system, its entropy increases. And if heat is rejected from the system, then dq will be negative, then ds will also be negative. So if heat is going out to the system, from the system, then dq is taken as negative, so ds will also be negative. It means when heat is going out from the system, entropy of the system decreases. For a reversible process, if a system goes from initial state I to final state F, then total heat which is absorbed or rejected is given by Q equal to integral Tds, and integral is for I to F, from initial state to final state F. So if a system goes from initial state I to final state F, total heat absorbed or rejected is given by this integral Tds. This is from this relation because dq is Tds. So q will be equal to integral dq, that is integral Tds. And this integral Tds will be equal to the area between Ts curve and S axis. If we plot a graph between T and S, and temperature T and entropy S, then this integral Tds will be equal to the area between this Ts curve and S axis. Graph plotted between temperature T and entropy S is known as temperature entropy diagram or TS diagram. This is the Carnot cycle in PV diagram, that is indicator diagram, and this is also Carnot cycle, but now it is plotted between T and S, between temperature and entropy. So it is TS diagram or temperature entropy diagram. In Carnot cycle, there are four processes. First is AB, that is isothermal expansion at constant temperature T1. T1 is the high temperature of heat source. So in this process, working substance absorb Q1 heat from heat source at constant temperature T1. So in this process, entropy of working substance will increase because working substance is absorbing heat from heat source, and this increase in entropy will be equal to Q1 upon T1 from this relation. dq is Q1 and T is T1. Then ds change in entropy is Q1 upon T1 from this definition. And this change in entropy ds, if we assume that initially entropy is S1 and finally it becomes S2. At point A, entropy we assume as S equal to S1, and at point B it is increased and let it become S2. So S2 minus S1 is ds, change in entropy, and this S2 minus S1 change in entropy is equal to Q1 upon T1. In the next process, that is adiabatic expansion, process BC, there will be no change in its entropy because in adiabatic expansion there is no exchange of heat. dq is 0. So ds is 0 from this definition of entropy. In the third process, CD, which is isothermal compression, this process is at constant temperature T2. T2 is low temperature of sink. In this process, working substance gives Q2 heat to sink. So entropy of working substance will be decreases, and this decrease in entropy will be equal to Q2 upon T2. But this Q2 upon T2 is same as Q1 upon T1, which was the increase in entropy in the first process AB, that is isothermal expansion. So in first process AB, if entropy increases from S1 to S2, then in this third process CD, the entropy will be decreases from S2 to S1. This change in entropy is same, which is Q2 upon T2 and which is equal to Q1 upon T1. These are equal. Q2 upon T2 is equal to Q1 upon T1 for Carnot cycle. So change in entropy is same from A to B and C to D. In the process AB, it is increases from S1 to S2. In the process CD, it is decreases from S2 to S1. And the fourth process is DA, that is adiabatic compression. In this process, there is no exchange of heat. dq is 0. So from this relation, ds is also 0. In this way, this Ts diagram will be a rectangle. In the first process, in which entropy it changes from S1 to S2, it is at constant temperature T1. So this AB line will be a horizontal line. And in the next process BC, which is adiabatic expansion, in this process there will be no change in entropy, so entropy remains the same, that is S2. But in this process temperature is decreases from T1 to T2. In the process CD, again entropy is decreases from S2 to S1 and temperature is constant, that is T2. And in last process DA, for adiabatic compression, entropy remains the same, that is S1, and temperature increases from T2 to T1. In this way, this TS diagram will be a rectangle as shown in this figure. Now we can calculate the heat extracted from source during isothermal expansion. The process AB is the isothermal expansion. In this process, working substance extract Q1 heat from heat source, and this Q1 heat will be equal to, from this formula, integral Ts, and it will be equal to area between Ts curve and S-axis. So area between Ts and S-axis will be the area of ABFEA curve, and this area ABFEA will be equal to T1 into S2 minus S1. AE is equal to T1 and EF is equal to S2 minus S1. So Q1, which is equal to area ABFEA, and this area is equal to T1 into S2 minus S1. So heat extracted from source Q1 will be equal to T1 into S2 minus S1. Similarly, in this process CD, which is isothermal compression, in this process working substance rejects heat Q2 to sink. So this heat rejected to sink in this process CD, Q2 will be equal to the area of this curve between CD and S axis. So this will be equal to the area of curve CDEFC, and area of this curve will be equal to T2 into S2 minus S1. DE equal to T2 and EF equal to S2 minus S1. So Q2, heat rejected to sink, is equal to area CDEFC, and this area is T2 into S2 minus S1. Now the work done during one cycle, work done will be equal to W equal to Q1 minus Q2. If working substance absorb Q1 heat and it rejects Q2 heat, then this remaining heat, which is Q1 minus Q2, is converted into work. And from these two relations, we put the values of Q1 and Q2. Then this work done will be equal to T1 minus T2 into S1 minus S2. And this is the area ABFEA. This is the area AB. It will be equal to the area ABCDA. It is the area of this TS diagram, because AD is T1 minus T2 and CD is S2 minus S1. So T1 minus T2 into S1 minus S2, it is the area ABCDA. Now, so in TS diagram, area of rectangular curve represents the work done. Now we can find out the efficiency of Carnot engine. This is the formula for efficiency. Efficiency eta is equal to work done divided by heat taken, Q1, and work done is Q1 minus Q2. So it is Q1 minus Q2 upon Q1. We put the value of Q1 minus Q2 from this relation, which is equal to T1 minus T2 into S1 minus S2, and put the value of Q1 from this relation, which is T1 into S2 minus S1. Put these values here, and we get this efficiency equal to T1 minus T2 into S1 minus S2 upon T1 into S2 minus S1. So correct here, it is not S1 minus S2, it is S2 minus S1. In this expression for W equal to Q1 minus Q2, it will be equal to T1 minus T2 into S2 minus S1. S2 is greater than S1 and T1 is greater than T2. So it is not S1 minus S2, it is S2 minus S1. So here also we have Q1 minus Q2 equal to T1 minus T2 into S2 minus S1 upon T1 into S2 minus S1, and S2 minus S1 will be cancelled out in numerator and denominator, and the remaining term is eta equal to T1 minus T2 upon T1, that is 1 minus T2 upon T1. Entropy is related to disorder. Entropy is a measure of disorder of the system. If disorder increases, then entropy is increases. Now, third law of thermodynamics. Nernst propounded third law of thermodynamics, according to which at absolute zero temperature all the processes of a system occur such that there is no change in entropy of system, or in other words we can say that if a system is at absolute zero, T equal to 0 degree Kelvin, its entropy will be a universal constant which we can assume as equal to 0. So from third law of thermodynamics we see that at absolute zero temperature, at T equal to 0 degree Kelvin, entropy S can be assumed as equal to 0. Now we consider this question. We want to find the change in entropy when 1 gram ice of 0 degree centigrade is converted to steam at 100 degrees centigrade. What will be the change in entropy? So we are converting 1 gram ice of 0 degree centigrade to steam at 100 degree centigrade. For this, we assume three processes. In first process, we convert this 1 gram ice of 0 degree centigrade to 1 gram water of 0 degree centigrade. Temperature remains same, 0 degree centigrade, and we convert this ice into water. We convert solid state into liquid state. In this process, the heat given to ice will be the latent heat, and the change in entropy delta S1 will be equal to mL upon T. It is not C, write it as capital L, which is latent heat. mL will be total latent heat for m gram substance, L is latent heat for 1 gram substance. For ice, its value is 80 calorie per gram. It is not 30, it is 80 calorie per gram. If ice melt into water, then latent heat required for this is 80 calorie per gram. Multiplied by mass, this is total heat required, it is ml. M is 1 gram, so it is 1 into 80. And this process is at constant temperature, which is 0 degree centigrade, which we convert into Kelvin, that is 273 degree Kelvin. So delta S1 change in entropy is ml upon T. It is 1 into 80 upon 273 and it is equal to 0.29 calorie per gram. Latent heat L is 80 calorie per gram. Correct this, L is not 30, it is 80. Now we convert this water of 0 degree centigrade to the water of 100 degree centigrade. Now the state remains the same, liquid state, and we want to increase the temperature from 0 degree centigrade to 100 degree centigrade. In this process, change in entropy delta S2 is given by this formula mc log T2 upon T1. This formula for change in entropy mc log T2 upon T1 comes from the definition of specific heat C. C is a specific heat, and definition of specific heat C comes from the formula dq equal to mc dt. Heat required to change in temperature dt, dq will be mc dt. So delta S2 will be equal to ds is dq upon t and dq is mc dt. So delta S2 can be obtained by integrating this, and by integrating this we get mc integral dt upon t. And integral dt upon t is log t, and if we put limits from t1 to t2, it will give log t2 minus t1, that is equal to log t2 upon t1. So change in entropy delta S2 now will be mc log T2 upon T1. M is 1, mass is 1 gram, C is also 1. The specific heat of water is 1 in CGS system. Convert this log E into log 10 by multiplying 2.3026. And it will be 2.3026 into log 10 373 upon 273. T2 is 100 degree centigrade, that is 373 degree Kelvin, and T1 is 0 degree centigrade, which is 273 degree Kelvin. Now it is equal to 2.3026 into log 10. This log 10 373 upon 273 can be written as log 10 3.73 upon 2.73. So this will be equal to 2.3026 log 10 3.73 minus log 10 2.73. Put the values of these logs from log table, and we can obtain this change in entropy delta S3 equal to 0.21 calorie per degree Kelvin. And at last we want to change this 1 gram water of 100 degree centigrade to 1 gram steam of 100 degree centigrade. Now the temperature is same, 100 degree centigrade, that is 373 degree Kelvin, but state is changed. We are changing the state from liquid state to vapor state. We convert this water into vapor. So change in entropy when 1 gram water at 100 degree centigrade is converted into steam. Steam is gaseous state. So we are converting liquid state into gaseous state at same temperature, that is 100 degree centigrade. In this process the heat required will be also equal to latent heat. So delta S3 change in entropy will be ml upon T. ml is dq, which is equal to the heat required for this change in state at constant temperature T. M is 1 gram and L latent heat for vaporization is 540 for water, 540 calorie per gram, and mass is 1 gram. So total latent heat will be ml 1 into 540. Capital T is 373 degree Kelvin, that is 100 degree centigrade, and it becomes 1.44 calorie per gram. So change in entropy when 1 gram ice at 0 degree centigrade is converted to steam at 100 degree centigrade will be equal to delta S equal to delta S1 plus delta S2 plus delta S3. By adding these three changes, we get delta S change in entropy equal to 1.94 calorie per degree Kelvin.